there are some alcohols. See, I am not saying all alcohols. Usually, alcohols with lower molar mass has more solubility, okay, compared to alcohols with a higher molar mass. So, some alcohols, phenols, some aldehydes with lower molar mass, some ketones and amines with lower molar mass. Usually, they dissolve in water very much. They have good solubility in water. But the point is, these are organic compounds. These are not supposed to be dissolved in water. Then how can these organic compounds are dissolved in water? Yes, that is because of hydrogen bonding. So, the concept of hydrogen bonding can explain why these particular organic compounds are dissolving. They are soluble in water. So, let me explain with an example. For suppose if I take ethyl alcohol C2H5 OH. Okay, and I hope you know oxygen has two lone pairs, and you know very well that compared to hydrogen, oxygen has more electronegative. So then partial minus charge, partial plus charge, you can take like this. Now you have to observe carefully. When hydrogen is present on oxygen, when hydrogen is present on oxygen, this hydrogen can have hydrogen bond with others. Now when you try to dissolve this ethyl alcohol in water, usually this ethyl alcohol molecule can form hydrogen bond with water molecules like this. I am taking a water molecule here. Okay, so partial plus charge, partial plus charge, partial minus charge, though finally the partial plus charged hydrogen, partially positive charged hydrogen of alcohol can form a hydrogen bond with oxygen of the water molecule. Like this can form another hydrogen bond with another alcohol, you can say like this. So this is the approximate way of representing how a alcohol is forming hydrogen bonds with water molecule, then this hydrogen with other, like this. So this is the reason instead of being a organic molecule, these compounds are dissolved in water. And similarly you can expect for phenols also. For phenols there is a hydrogen present on oxygen, you can expect hydrogen bonding. And for aldehydes, for suppose aldehyde, here there is no hydrogen on oxygen, but still this oxygen is bonded to carbon through the pi bond. So obviously compared to carbon, oxygen is more electronegative. Compared to carbon, oxygen is more electronegative. Then you can have this, you can assign a partial negative charge to this oxygen and partial positive charge. Fine. Now this partial negative charged oxygen can have a attraction with the hydrogen of water molecule which is having partial positive charge. Okay, like that amines also. If you take a basic amine, like fundamentally in amine, I am taking primary amine as an example. Primary amine means when nitrogen has two hydrogens, NH2, primary amine. Okay, fine. Now here you have to observe carefully. Hydrogen is present on more electronegative nitrogen. Then obviously this is partial minus, partial plus, partial plus. Now when hydrogen is present on more electronegative nitrogen, it can involve in hydrogen bonding with others. So simple consequence, simple explanation to the fact that instead of being organic compounds, some organic compounds are very much soluble in water because of hydrogen bonding. And the next consequence of hydrogen bonding, or the next fact we are going to explain with the help of hydrogen bonding, is the high melting points and boiling points of hydrides of nitrogen, oxygen, fluorine. So first of all, we must know what is a hydride. Hydride of an element. Hydride is a binary compound. Hydride is a binary compound. Binary compound of hydrogen with other element. Okay, sir, what is binary? We don't know, sir. Binary means there is two components, two elements for sec. So H2O, it is a binary compound made up of two elements. NH3, binary compound made up of two elements, and HF, two elements, binary. But in these binary compounds, just one element is compulsory hydrogen, then it is hydride. Fine. Now let's move towards what is the fact we are going to explain with the help of hydrogen bonding. See, usually when you take the hydrides of any of these family members, let's take 50A group elements. Let's take 50A group elements. 50A group elements means what? Nitrogen, phosphorus, arsenic, antimony, bismuth. Nitrogen, phosphorus, arsenic, antimony and bismuth. These are the 50A group elements. Now I am going to take hydrides of 50A group elements. Hydrides of 50A group elements means NH3, PH3, ASH3, SbH3, BiH3. Okay. Usually you may came across about the names of these hydrides in the higher studies, but I'll give you the names for now. The name of this compound is ammonia. Next one, phosphine, arsine, stibine, bismuthine. Phosphine, ammonia, phosphine, arsine, stibine, bismuthine. So okay, forget about the names. All these are hydrides. Hydrides of 50A group elements or 15th group elements. Now, if you have to give answer regarding what is the order of boiling points or melting points in these hydrides, if you have to know the increasing order of boiling points or melting points, or the decreasing order of boiling points or melting points, usually how we can think? See, generally between molecules there is some attractions. Between molecules there are some attractions called van der Waals attractions. Between molecules there are some attractions called van der Waals attractions, and the amount or the magnitude of that van der Waals attractions usually depends upon molar mass. So more molar mass, molecular weight you can take, molecular weight. More is the molecular weight, more is the attractions. When more is the attractions, more will be the molecules associated. So when molecules are very much associated, we need higher energy to melt that solid or to vaporize that liquid. So the point is, if in a liquid there is more attractions, if in a liquid there is more intermolecular attractions, we need very high temperature to vaporize that liquid. So simply, more is the attractions, more is the boiling point. But the attractions are because of more molar mass. More molar mass, more attractions. Next point, for solids also, melting points also same thing generally. More is the molar mass, more is the attractions. more attractions, more in the concept of solids, there is another factor called packing also, packing. Okay, so more is the attractions, more will be the melting points also. Okay, with that point, what is the order of increasing boiling points in this? So if I take y-axis, x-axis, on x-axis I am taking, let us take atomic, that means atomic mass of fifth A group elements, I mean nitrogen, okay, nitrogen, phosphorus, arsenic, antimony, like that I am taking. And on y-axis I am taking boiling points or melting points you can take. Then what you expect? What is the order? So as the atomic number increases, or the molar mass increases, you can take molar mass on x-axis, So as the molar mass increases, intermolecular attractions increases. As the molar mass increases, intermolecular attractions increases. If intermolecular attractions increases, boiling point has to increase. Then what is the order you expect? You expect the order will be like, I am writing here first, the order will be like, from the molar mass point of view, from the intermolecular attractions point of view, basing on the molar mass, compared to ammonia, phosphine has more boiling point. You expect that. So this is our expectation. This is our expectation based on the molar mass and the resultant intermolecular attractions based on molar mass. But the reality is different. The practically observed boiling point values show something different, which is, I am giving now, ammonia has more boiling point than any of the members. Okay, this is the fact, this is the reality. We need to explain this. Yes, now we are going to explain this fact with the help of hydrogen bonding. Simple fact. In rest of the members, there is only van der Waals attractions, normal intermolecular attractions. But in the first member, there is, along with the van der Waals attractions, there is one more powerful attraction than van der Waals, which is hydrogen bonding. Why, sir? Yes, in the first member, hydrogen is present on nitrogen. I told you that when hydrogen is present on nitrogen or oxygen or fluorine, you can expect hydrogen bonding. So that's why you can normally, without hydrogen bonding concept, you expect the boiling point or melting point order like this: NH3, PH3, ASH3, SBH3, BiH3, like that you can expect. But in reality, because of hydrogen bonding concept, the boiling point or melting point of NH3 will be like this. Okay, this way. So NH3, PH3, ASH3, SBH3 and BiH3, and for the rest of the members, for the oxygen family or halogens also the same thing. For the halogens also same thing, HF also. Okay, that means, let me take the next page. See, the boiling point order of, take the hydrates of 17th group elements, HF. First of all, I'll write the 17th group element: fluorine, chlorine, bromine, iodine. HF, HCl, HBr, HI. These are the hydrates of. Now tell me, depending upon the molar mass, what is the increasing order of intermolecular attractions? Yes, molar mass is increasing in this direction. Intermolecular attractions also will increase in this direction. So we expect that attractions and the melting points and boiling points has to be in this order, right? This is our expectation based on only molar mass and the resultant intermolecular attraction based on molar mass. But reality is different. In reality, HF is going to have more melting point and boiling point than the rest of the all members. Why? The same reason. All of them are having only van der Waals attractions based on molar mass. But for the first member, along with the normal attractions, there is one more kind of attraction, that is hydrogen bond. HF has hydrogen bond. Okay, so this way we can explain the unusual high melting point or high boiling point of the first member compared to the rest of the members in these families. Okay, but you can support this application with another observation of the 14th group also. See, if I take 14th group members, carbon, silicon, germanium, tin, lead. Okay, take the hydrides of 14th group members, CH4, SiH4, GeH4, SnH4. Theoretically, I am taking hydrides of all of them. Okay, theoretically I am taking. Now, what is the increasing order or decreasing order of the boiling points or melting points of these fellows? Usually, you expect from the molar mass point of view, molar mass increases down the group. So, you expect this is the melting point order. Okay, and your expectation is correct. This is the order. And here, the first member also according to the expectation. So, no change like this. So, the order you expected is correct. Why, sir? Why? Because in the first member or in the rest of the members, in all of them, hydrogen is not present in any of the three, the nitrogen or oxygen or fluorine. Okay, I hope you understand this. And the next observation I am going to explain is, see, there are isomers like orthoisomers and para isomers you may heard in organic compounds. Among isomers, one isomer is more volatile and another isomer is less volatile, or one isomer has more boiling point and another isomer has less boiling point. These kind of examples you may came across. Yes, we can explain those facts also, some of those facts with the help of hydrogen bonding. So I'll take one of them. Why orthonitrophenol, or why orthonitrophenol has more volatility compared to paranitrophenol. Okay, let me explain this. So this is the fact. The first point is, compared to paranitrophenol, orthonitrophenol is more volatile. I hope you know what is volatility. I explained in vapor pressure concept, solutions chapter, colligative properties. Okay, yes, more volatile means great tendency to get into vapor phase. Okay, more volatile liquid means that liquid has comparatively more tendency to get into gaseous phase. Yes. What is orthonitrophenol? Simple. You take phenol and at ortho position you take NO2 group. Okay. Now the point is, there is a partial negative oxygen, partial positive charged hydrogen, partial negative charged oxygen. So there is a hydrogen bond, but you observe carefully, this hydrogen bond is nothing but intramolecular. I explained previously, intramolecular. What I mean by intramolecular? Here the hydrogen bond is present between two different groups of the same molecule. Now, if you take the same compound, that means same molecular formula but different arrangement, paranitrophenol, that means OH and NO2 groups are at para positions. I hope you know what is para positions. 1, 2 positions, first position and the next position. You can take on this side also. 1, 2 positions are called ortho positions. Here these two groups are ortho to each other. Yes, and this is 1, 4. 1, 2, 3, 4. 1, 4. Paranitrophenol. Orthonitrophenol, paranitrophenol. Now here also you can expect hydrogen bonding, but the point is this OH, this hydrogen can't have hydrogen bond with this nitrogen. Obviously this hydrogen has to form a hydrogen bond with oxygen of other molecule. Here also this oxygen also has to form hydrogen bond with hydrogen of other molecule. Not here, hydrogen bond is not present inside the molecule. Here hydrogen bond is present in between molecules. This is intermolecular hydrogen bonding. Intermolecular hydrogen bonding. So the point is, when there is intermolecular hydrogen bonding, means hydrogen bond between molecules, what happens? So many molecules are associated. So many molecules are associated as a group, so they present together. So it becomes a little bit tough to break those attractions and vaporize the molecule. Or get the molecules into the gaseous phase. Comparatively here what happens? The attraction is between two groups of the same molecules, but this molecule is present individual and another molecule is present individual. They are separated. So if you supply some energy, easily one molecule gets into vapor phase easily, but here to vaporize this molecule or to get this molecule into the vapor phase, you need to break these hydrogen bonds. So that's why the boiling point of this para isomer is more than this one, orthoisomer. So I hope you remember, more is the boiling point, less is the volatility. Right? So orthoisomer is more volatile. More volatile means less boiling point compared to para-isomer. So with the help of hydrogen bonding, we understood or we are able to explain this fact. This is a fact, it is reality. But with the help of hydrogen bonding, we are able to explain that reality. I hope you understand this consequence also. Now, one more observation about water, which we can only explain with the help of hydrogen bonding. Yes, usually we know that solid has more density. Solid has more density than liquid, right? Everyone knows, everyone generally, than liquid. Why sir? In solid compared to the liquid, what happens? In solid, particles are very much closely packed. That's why compared to any liquid form of a matter, you take a compound, particular compound. I am taking particular compound and imagine that particular compound in liquid state and solid state. Then usually what you guess? In the liquid state, the particles are comparatively very much far away. So the density will be less. In the solid form, what happens? The particles are close enough, so the density is high. So usually we expect, or usually we know that solid has more density than liquid. But there is an observation: ice floats on water. But ice floats on water. See, ice is the solid form of H2O. Ice is the solid form of H2O, water is the liquid form of H2O, right? Then if according to the above observation, above statement, or according to the above fact, if solid has more density than liquid, then why ice floats on water? Yes. So this phenomena, this observation, it's a fact. We need to explain this fact. So this fact also we can understood with the help of hydrogen bonding also. See, in the case of water molecules forming solid substance, solid ice, what happens is, to form the hydrogen bonding, we need a particular geometrical arrangement. So let me explain. In water molecule, in ice, H2O molecules are arranged in tetrahedral manner. Tetrahedral manner. See, I will give you approximate tetrahedral arrangement to understand it better. I hope you know this is the tetrahedral arrangement. Yes, that is the tetrahedral arrangement. See, I hope you understand. This is this line is coming towards you, and that yellow color line is going away from you. Okay, I hope you understand. So that's why I use different colors. Now the point is, H2O molecules are at corners. H2O, that means at every corner there is H2O molecule. H2O. But the point is how they are associated. 1, 2, 3, 4. I have taken 4. How they are associated? See, if I take a oxygen molecule like this, then this will be one hydrogen, this will be another hydrogen. I can take like that, no problem. If I take like that, then obviously this hydrogen has to form a hydrogen bond with other oxygen of the other molecule. So immediately I have to take oxygen here, but I can't take one hydrogen here because hydrogen can't have hydrogen bond. So simply I am taking one hydrogen to the upper side and another hydrogen to this side. So what you can guess? So now this dotted line indicates what? This dotted line indicates hydrogen bond. This solid line indicates normal bond. This dotted line is hydrogen bond. Let me give you a different color to it, please. So this is the hydrogen bond. Yes. So as there is hydrogen here, I can take only oxygen. Yes. Oxygen. Okay. Now, as there is hydrogen, I need to take a oxygen here also. Oxygen. And oxygen and hydrogen bond. And if I take one, yes. Now the point is, now this oxygen is forming a attraction. I can take an attraction like one hydrogen to this side and another hydrogen to this side. There is an attraction. I made a mistake here. Hydrogen can't have a hydrogen bond, so I can take this as, let me give some time. Yes. Now see, I have given an approximate tetrahedral arrangement in which the 4 water molecules are in hydrogen bonding. See here, this water molecule, you take this water molecule. This is, I told, every water molecule is bonded to 4 other water molecules through hydrogen bonding. One is this one, another can be other molecule outside this tetrahedron, and one. See, I'll use the same. Let me use the same green color. Hydrogen bond 1, 2, and there is a hydrogen bond 3, and there is a hydrogen bond 4, like this. Okay, like this. Now this water molecule, hydrogen bond with other hydrogen bond, one hydrogen bond with other H2O molecule outside the tetrahedron, other one, like this. This also. Okay, like this. So this way every water molecule is involved in this tetrahedral structure. Now what happens with this? See, imagine compare here, between this oxygen and oxygen there is two bonds existing. One is the strong covalent bond, another one is the weak hydrogen bond. Okay, so when the bond is weak, the length will be high, na? More is the length, less is the strength. So because of this hydrogen bond attraction, they are a little bit far away. So for the structure to form, there must be some gaps. There must be some gaps between the molecules. If that gap is not present, if this much gap is not present between these two water molecules, hydrogen bond is not possible. If hydrogen bond is not possible, solid formation is not possible. So to maintain this much gaps, for the formation of hydrogen bonding, water molecules will be this much far away to form this structure. So you can see simply there is lot of empty space. Because of that empty space only, in solid ice there is less density. See, imagine if these water molecules are closely packed, then density will be usually high. So that happens when you melt this ice. When this ice melts, what happens slowly? When this ice melts, slowly these hydrogen bonds breaks. As the hydrogen bonds breaks, the water molecules comes close together. As the water molecules coming close together, the density of ice slowly increases. The density of water increases, and that reaches maximum at a particular temperature. See, usually at 0 degrees there is ice. 0 degrees Celsius there is ice, and when melting starts means you are heating. When heating starts, slowly this hydrogen bonds breaks. When the hydrogen bonds are breaking, water molecules are coming close together. Slowly density increases. Density increases at 4 degrees. The density of water becomes maximum, which is 1 gram per cc. Okay, so that's why usually we take density of water as 1 gram per ml. 1 ml is 1 cc. Okay, 1 gram per ml. That means we are taking the density of water which is considered as a maximum at 4 degrees Celsius temperature. Okay, I hope you understand. Now the last consequence, but not the least consequence. The last consequence, that means I am discussing this consequence of hydrogen bonding at the ending. Okay, but this is the most important consequence of hydrogen bonding. In fact, this is the concept because of which today we are existing on earth. In one way I can say that because of this point, because of this consequence of hydrogen bonding, today we present on earth. Today life exists on earth. See, you know, life exists on earth because of presence of water. Imagine if water is not present, then there is no life. Yes, let me explain. See, there is an observation why or H2O is liquid and H2S is gas at normal temperature, at normal condition. See, this is an observation. Why H2O is liquid and H2S is gas at normal conditions? Sir, you may ask me, sir, why you comparing H2O with H2S, sir? Yes, H2O, H2S, both are the hydrates of the same family, na? Oxygen, sulfur, selenium, tellurium, polonium, right? OH2, yes, I'll write like this. H2O, H2S, H2Se, right? So oxygen, sorry, H2, yes, H2O, H2S, H2Se, oxygen, sulfur, selenium, tellurium, polonium. So oxygen and sulfur belongs to same family, and H2O and H2S are the hydrides of same family. But still, at normal conditions, H2O is existing as a liquid, but H2O is existing as a liquid, H2S is existing as a gas. So, by the way I am asking the question, you may get the clarity about the reason also. I believe. See, what is the difference? Here, in H2O, hydrogen is present on oxygen. In H2O, hydrogen is present on oxygen. But in H2S, hydrogen is present on sulfur. Okay? Sir, see, you can make the these lone pairs at any positions, okay, normally, yes, but what makes it different? Yes, hydrogen, when hydrogen present on oxygen, there is a hydrogen bonding, yes. Now, this hydrogen can form a bond with a hydrogen bond with other oxygen, and this one can form a hydrogen bond with other oxygen. This oxygen can form, because of this lone pair density, this can form a hydrogen bond with other hydrogen of the other molecule. This also can form a hydrogen bond with the hydrogen of the other molecule. Okay, fine. Yes. This way you may get a question, how many hydrogen bonds a water molecule can have? Yes, 4. A single water molecule can associate with 4 water molecules through hydrogen bonding. But the point is, because of this association, water molecules are in groups. The water molecules exist as in groups. That means water is existing in liquid state because of these intermolecular attractions called hydrogen bonding. And that kind of intermolecular attractions are not present in H2S, because hydrogen is present not on sulfur, not on nitrogen or any oxygen or fluorine. It is present on sulfur. So in the H2S you can expect only van der Waals attractions, which are very weak enough. So normal conditions are enough to vaporize the H2S. Okay, so that's why at normal conditions H2S is existing as a liquid and H2S is existing as a gas, while H2O is existing as liquid.